Hi, this is Dr. Touch. Today I want to demonstrate how I constructed an attitude-independent compass bearing for my DT augmented reality controller. The problem being, if you look at the iPhone, the general compass is more or less straight out at the top. So if you have the device like so, or even flat, it's easy to get a compass bearing. If it's on the side and you basically look into the screen from one side, then you can simply add 90 degrees and you would have like the compass like that. But the problem is, with an augmented reality application like I'm planning to do, you could also turn the iPhone like that, or even look up and down. And the problem is, if you turn it 90 degrees like that, you get a 90 degrees of compass bearing. So that was of no use. Fortunately enough, for the internet, I found a paper somebody had written on it, and it gave me a great idea how I could get a compass bearing that's independent from the attitude of the iPhone. That is by means of the accelerometer. Basically what you're doing is, if this is my iPhone, I always have gravity as a vector coming out of this corner of my iPhone here. So if I'm moving it around, it always points in the same direction. There's another vector that I get with the 3GS that is a magnetic vector, and it's pointing north in an angle of about 60 degrees here in Central Europe. It's not pointing horizontal because everybody, if you learn this at school, you know the magnetic field is not parallel to the Earth. That's only at the equator. The further north you get, the further down it points, and that's called inclination. And that's one thing you can use as well. So how do we get our compass bearing? It's a little bit of vector mathematics necessary. First, I take my vector pointing to the North Pole. I take my gravity vector, and then I do the so-called cross product. And the cross product basically gives me a third vector that's perpendicular to the other two. And in our case, that's exactly horizontal because it's right angled to gravity, and it's pointing east because it's right angled to the north vector. So here's one vector that you can use, horizontal east. If I were to cross product it again with gravity, I would get a horizontal north vector. But we don't care about that. As long as it's horizontal and it's a compass, it's sufficient. You see in a second why. Now with the iPhone, you can look up and down and turn it. So the looking vector I decided to be 0, 0, -1, basically coming straight out at the back, or actually at the corner where there's 0, 0, x0, y0. So this is my looking vector, could be pointing, say, up. Again, I take gravity, mount it here. Again, I do a cross product, so I get my third vector, and in this case, that's horizontal to the right. So however I look up or down, this is always going parallel to the floor, and it's to my right. Now what happens is I have two vectors, a horizontal east and a horizontal right, and the only thing I need to do is do a arccos cosine of the dot product of those two, et voila, I get my compass bearing. Now that's a little bit complicated. Let me show you how this works out in practice. I still have my iPhone application here. You can see if I turn it a bit, do we find, there it is, our Steve Jobs. And what happens is, okay, I can look up and there he disappears. I can look down, it disappears as well. And what I can do now is I can also slowly rotate it. And you see the bearing is basically rather independent from, oops, it's a little bit difficult to record it like that, sorry. So it doesn't matter which way I'm holding the iPhone, Steve is always at the same position. So and another thing I want to briefly demonstrate is this Steve icon here is nothing but a button, so I can even push him and you see he gets dark, because that's the default behavior for buttons, and I could do an action related to this icon. Another thing you currently see, it's not just the trembling of my hand that he jerks around like that. That's a little bit of a problem with the calculation. It's so exact that it also accounts for variances in the magnetic fields, of which there are plenty, let me tell you. And one thing that I probably have to do finally is do some further smoothing. If I detect that the iPhone is not being moved, then I could maybe freeze the compass so that it doesn't move around like that. But what's happens currently, if I move the iPhone, he moves very quickly. So I like to get this responsiveness, but I want to get rid of the jerkiness in the end. So what's left to do here? Well, only a couple of things until the first public version basically can be released. Maybe a little bit of the smoothing that I talked about, and then have the appropriate interfaces so that you can use this DT augmented Realtiy controller very easily in your own product. You basically pass it the icons and the geographical locations and maybe a cut of distance, and it would display these icons in a fashion that you like. One thing, currently it's just a button, so basically you could do that with any view. You could put a bubble view that moves around and maybe updates the distance, or maybe you could take a button, just like I did in this case. I think I'm going to make it in a way that this is customizable, and only thing you need to do is add a delegate method to your custom view, so that the view also has a geographical location, and the DT Augmented Realtiy View Controller will do the rest. So I hope you enjoyed it. Stay tuned.